Hi, good morning everyone. Welcome to the class ECE451 Control Engineering. On Monday we just finished the second midterm exam, and now we will study the next chapter, chapter 7, state space design. Okay, so this chapter we will use a different way to describe the system, which we need more calculation on the matrix steps. Right? ECE451. ECE451. This will be which week? The Wednesday of the ninth week. Stay space design. This is chapter 7 of the textbook. Okay, so first about what is the state space? State space. So this is we use a different way to describe the system. So we have the state space description of a system. The most general forms look like this. It's d over dt x of t equal to, here's a f of x of t and u of t, and y of t equal to some g of x of t and u of t. Okay, this is the general form, where x of t, it is a vector. It is x1 of t until some x, suppose n, xn of t. This one this is state variables. State variables. We have n state variables, and u of t is also a vector. It's u1 of t until u. Okay, I use a p of t. So they are input signals, input variables. Let me say A. Okay, and y, it is also a vector. It's a y1 of t until like ym of t. They are the output variables. So in general, you see the system now we have p input. Maybe one input, maybe multiple input, and m output. If m is 1, then you have only one output. Maybe m is larger than 1, then you have multiple output. So this one can use to describe both the single input, single output system, or multiple input, multiple output system. So can use for both. For both single input, single output, or multiple input, multiple output system can be used for both these two kind of system, depending on the P and L. If this is 1, then it's a single input, single output. If they are larger than 1, either one larger than 1 or both larger than 1, they are multiple input, multiple output system. And here these two equations, this one we call this is the state equation. State equation. State equations. Equation are equations. And this is output equation. And f and g, they are all vectors. F, g, vectors of functions. We can have example. Like x1 of t, x2 of t, take derivative, equal to like x1 of t plus sine of x2 of t plus u1 of t, and here's t squared times x1 of t plus x1 of t times x2 of t, and plus 3 u1 of t and minus u2 of t, like this. Then f, this is f, this is capital F, so some x, some u. This capital F, actually you have two functions, right? Two functions you listed as a vector, and all of these, they are state equations. And you also need an output equation, like y1, y2 equal to x1 plus x2 and x1 minus x2 plus u1, for example. Yeah. Then this is g. This is g. This is g. All right. So this is we call this is the state description of the system. We have state equation, we have output equation, we have two state variables, two input x1 and x2, and two output. So this is a MIMO system, right? This is a MIMO system. All right. Now let's consider the system actually we were studying. This is more general, right? This is generally any kind of f and g. And if this one, so we call this linear system. What is the linear system? Linear system can be described by this: x of t or equal to this part we can write as like a of t times x of t plus b of t times u of t, and y of t were equal to c of t times x of t plus d of t times u of t, like this. Here you see this side we have x and u. They are just the first order, not zero order, that will be constant, not higher order, that's a square or something. And of course also we do not have the functions like a sine of t, cosine of t, like here I have sine of x2, right? So we don't have those kind of things. We only have x, u. So this is a linear. It's a linear. A, B, C, D, they are matrix, but matrix of functions of t. Okay. A, B, C, D, now they are matrix of functions of t. Right. So this one we call it a linear system. And then LTI system, linear and time invariant system. It is a d of dt, x of t. First of all, they are linear, right? They are linear. So here's some a, but no t, because it's a time invariant. Time invariant, so these coefficients, they will not change. Will not change when t is changing, when time is changing. So they are constant matrix. X of t plus bt, no t, sorry, u of t, and y of t were equal to c times x of t plus d times u of t. So this is a time invariant. All these coefficients a, b, c, d, they were independent with the time. When time changing, they are fixed. So the behavior of the system will keep to be same when time is different. Time invariant. And also it's linear, right? Similar with this, it's linear and time invariant system. And we will focus like this in this chapter. We'll study these in this course. We will study this in this course. LTI system. We focus on this LTI system. For linear system, we have another class is a linear system. Just called linear system. Is 550. Yeah, ECE451. That is about a linear system. More generally, right? A, B, C, D. They might be changed. So maybe time invariant, maybe time variant. Right? And then more generally for this kind of things, more generally, of course, usually we consider non-linear case. Linear case is in the course linear system. For this one, we have another course is a non-linear system. So that course will focus on the system looks like in this way. Here f and g, they are non-linear. Similar like this example, right? You have sine of some t, sine of some x, and x1 times x2, right? These kind of things, they are not linear on the state variables. All right. Now we consider the first problem for the state space description of system. How to we want to find the state space description from differential equation. So far, in most cases, we describe a system by one differential equation, right? So now we try to consider how to find the state space description from differential equations. I use an example to explain it. Actually, we have different methods. The result is different. So, okay, example 1. Actually, this is the method 1, you can say. Method 1. We consider a system with differential equation like y 3 order derivative plus 2 order derivative with coefficient 2, and 3 times y derivative and 4 times y equal to r. R is the input. We want to write these in terms of the matrix form. So for this one, we can just simply work like this. Let x1 equal to y, x2 equal to y derivative, x3 equal to y with second order derivative. That will be enough. We need 3. This 3, because here is order 3. Order 3. On the derivative of the output, we have order 3. And this side is order 0. No derivative. Right. Yeah. For this kind of system, then we can just let those y and their derivatives as the state variables. We do not need the highest order. We need the y itself with 1 derivative, 2 derivative. That's it. Okay. Then we can have x1 take derivative. X1 take derivative is what? It is just y derivative, right? And y derivative is x2. Okay, so we can compare here. Okay. We want to write the system in terms like this. For the state equation, the left side, they are just the derivative of the state variables, and the right side, they contain the state variables and input with some relation, some function, right? So here we did it, we got it, right? This side is a derivative of one of the x, the state variable, and the other side we contain just the state variable, no derivative, just a state variable. Okay, so the first equation is good. The second one, similar thing, we consider the x2 derivative. Okay, I just put prime, that means derivative for t, right? x2 derivative, that is a y prime with another prime, so this is y with 2 prime. Okay, that is x3. Okay, we're done for this one. This is derivative of some x, the other side is also some x. Okay, we get it. And then x3 derivative, that is a y2 derivative with one more derivative is y with 3 derivative. Okay, this one you cannot use this, right? We do not have y with 3 derivative. But the original equation, we have y with 3 derivative here. Is this one, right? So we have this. So we just move this part to the other side and replace y prime and y2 prime by x1, x2, x3. Okay, so this is 4y. So this is a negative 4x1. And 3y prime is negative 3x2. And 2 with y2 prime, y2 prime is x3 is minus 2x3. And plus r. Here I put the x with the order, the index, order by the index from 1 to 2 to 3. So I put x1 first. I put this in the first. Alright. And what is y? Y is just x1. Okay, we have the equation. Now we have the equation. These three are state equations. And this one is the output equation. We can try to write these in the form, we say for linear LTI system, we can write in this way, right? This way. So we will try to write in this way. They are all in matrix form. All these A, B, C, D, they are matrix, right? So we write in matrix form. We have derivative of x1, x2, x3 equal to, here's a coefficient times x1, x2, x3, and x1 here is just x2, so this is 0, 1, 0, and x2 here is x3, so we have 0, 0, x3, and then x3 derivative, it is this one. I have negative 4, negative 3, negative 2, and plus r, so 0, 0, 1, r. Okay. And then y, I also write this in a matrix form. It's a 1, 0, 0 times x1, x2, x3. Alright, we get it. So this is the final form in a matrix way of the state equations of the system. We have this one. So this is the method. When you have here, you have just the r, just the input, or maybe you have some coefficient before r, no derivative on r, then you can work like this way. You just let these y prime, y2 prime as the state variables. Then you can have the matrix form. Of course, you can have some change. For example, you can use r x1 as y with 2 prime, x2 is y1 prime, and x1 equal to y. And you change the order of these three, then that means you have different x1, x2, and x3. Then you can have different form. The matrix will look like different. Alright. Yeah, that's your choice. That's your choice. The answer is not unique. Okay, this is the first method. But in this method, we have a requirement. In the input side, you only have the input itself. You can only have the input itself. If you have a derivative here, you cannot use this method. Now we check the second method. Example 2. Example 2. This also consider related with method 2. That this method will give us we call this is a controllable or controllable canonical form. So finally, we will have a form of the equations. We call this form as a controllable canonical form. For controllable, later I will explain what is a controllable. Now you just remember this kind of matrix form of system is called the controllable canonical form, the CCF. Right, CCF. We still use the similar equation: y3 derivative plus 2y with 2 derivative, 3 with y 1 derivative, and 4 of y itself equal to, but now I have 2r derivative plus 3r. Okay, we have this one. Now if you just let those y's as the state variables x1, x2, x3, you cannot treat about this one r prime. So we have to work in a different way. We have the transfer function firstly. TLS is numerator is 2s plus 3 and the denominator is s cubed plus 2s squared plus 3s plus 4. We have this one. Now we rewrite these in this way. I divide by s cubed, so I have 1 plus 2 over s plus 3 over s squared plus 4 over s cubed. This is denominator. Numerator also divided by s cubed. I have 2 over s squared plus 3 over s cubed. I write in this way. Then we give a structure. The next step, after we have the structure, we will have the difference. We have the state variable equations based on this structure. We can pick some signals from the structure from the graph and use those as the state variables. All right. So what kind of structure? You look at it here. This is transfer function, right? It looks like the transfer function of a system. When you have a structure, you should know the numerator and denominator. We have the gain formula. Remember the gain formula. Gain formula. What is gain formula? It will be summation of some mi times delta I over delta, right? This will be the transfer function. This will be transfer function. Mi related with the forward path. And delta I, they are related with loops. Remember? Yeah, you should remember this one, right? The gain formula. Okay. So here we can have a structure with these as a transfer function. That structure we need 2 forward paths, right? We need 2 forward paths. and we can have 3 loops. And when you write the dirt, remember the dirt, you need to consider single loop and pair of loops and triple loops, but you need to condition those loop pairs or triple of loops, they will not touch each other. Here for the simplify, we only consider dirt only contain those dirt, each loop contain each loop, and suppose there's no loop separate. All the loops they touch together, they combine, they have some common part. Then we only need to consider single loop. No loop pairs, no loop triples. Okay, so we can work like this. Look at here. We have 3 loops, each weighs s or s squared or s cubed. And we have 2 forward paths, we have s squared and s cubed. So we can think like we have 3 1 over s. We can put like this: 1 over s, 1 over s. We have 3 1 over s. Then the forward pass, one forward pass is just go ahead. This forward pass, this side is y. This side is the input. This gives us one of the forward pass. Actually, this one. We need 3 over s cubed, so you need to put this 3 here. 3 somewhere, so we put it here. We put it here in the back side. If you put different place, like you put to the front, there will be different style of the structure, and it is not CCF. For CCF, you have to put 3 here. Alright, you put 3 here. This is one pass. Another pass, we have 2 over s cubed, s squared, 2 over s squared. So we have 3 1 over s here. We only need 2. So that pass will go across 2 of these 1 over s, and with actual 2 here. So we can work like this. We go to here. Alright, I need a summation. I need a summation. Right, I need a summation, and I put 2 here. So this second pass, you see, r, start with r, then 2 of 1 of s, and with 2, then go to y. So along this pass, the gain is just 2 over s squared. Right? The first pass is a 3 over s cubed. Okay, they are the numerator, they are good. Now we need the denominator, we need 3 loops. 3 loops, you see, these 3 loops. So how to give these loops? And we suppose the loop will contain some part of the forward pass. So you see, all the forward pass contain this part. So the loops, the loops, the kind of feedback also contain this part. So we can have this. This is 1, right? This is 1. Here I need again -2. -2, 1 over s, right? 1 over s and 2. So this loop is -1 over -2 over s. Then in dirt, that is 1 plus 2 over s, right? So here I need a summation. And the second loop, I have 3 over s squared. So I use this s squared and 3. I still go to here. This is the -3, right? This is also loop, right? This is also loop. This loop is -3 over s squared. Then similar, last one, I need a 4 over s cubed. So which part? I put from here, which location is good? I need a location, I need a coming back. I can go from here, oh, both same, right? If I go back here, yeah, I go back, separate here. If I go to here, this is another loop, right? This will be another loop, so I have to separate here. Okay, so this is also a pass. This is a -4. Alright, now we have the structure. We have the structure. This way. We have the structure. Start with r, we have 2 forward pass, 3 over s cubed and 2 over s squared. They are in the numerator. And we have 3 loops, so 1 minus the first loop minus second loop minus third loop, we get the denominator. And we do not have pairs of loops. Right? All these loops, they have the common part, so they are not separate. They touch each other, so you do not consider those loop pairs. Also, you do not consider triple of loops. And in the numerator, the delta I, in delta I, you also need to consider loops, but you have a requirement all the loops in delta I will not touch the forward pass. Now the forward pass contain this part, and all the loops also contain this part, so they touch each other, right? So we cannot use any loop in those delta i's. So delta I is just one. Alright, we got it. This structure related with this transfer function. Then we can have the state equation. State equations. Of course, you need to give state. You can give state like this. We know the derivative. This is 1 over s, right? 1 over s is an integral. So you put the derivative in the front. This is x1 derivative and x1. And here is the x2 derivative and x2. This is x3 derivative, not cube. And here is x3. Yeah, the signal input inside this 1 over s and outside with 1 over s, right? Yeah. Okay. Now, no dot here. Now we have x1, x2, x3. We have 3 variables. You can imagine this is circuit. Then you measure the voltage here, voltage here. You use these 3 voltage as the state variables. Okay, the signal as a state variable. You measure here, you get output. You measure here, that is the input. Right. Okay. Now what is the state equation? We can write it here. X1 dot equal to x1 dot is a summation of these 4 things, right? So the first one is x1 times -2. Second is x2 times -3. And third one is x3 times -4. And the last one we have input r. Alright. This is x1 derivative. And x2 derivative, it is just x1, right? So x2 derivative, it is just x1. And x3 derivative, it is just x2. Okay. Finally, you have a y. Y is this one, x3, right? x3, here's a summation. x3 times 3 and x2 times x2. So it is I put x2 in front of x3. So 2 of x2 plus 3 of x3. Alright, now we have our result. That's it, right? Of course, we prefer in the matrix form. That is x1, x2, x3. Take derivative. We're equal to x1 derivative is -2 times x1. Then -3 times x2. Then -4 times x3. Here's x1, x2, x3, and x2 is x1, so x2 is x1, no x2, no x3, and x3 derivative is this is x2, I put it wrong, x3 derivative is x2. Okay. So This is a 0, 1, and 0. And x1 also contain one term of the input, like this. And finally y, also writing matrix form. This is 0, 2, and 3 times x1, x2, x3. Okay. So finally we have the matrix form of the system. Matrix form. And this is a controllable canonical form. This one is A, this is a B, this is C, and here's a D. Here's a D. For the controllable canonical form, they have something special here. B, it always looks like this. It's 1 and some zeros. The only first element is 1, then all the rest are zeros. This is B. And for A, the first line, the first row, you have some numbers. These numbers related with the transfer function. You see, this is 2, 3, 4. Here's a 2, 3, 4, but with a negative. And then other than these, you separate. Here's a unit matrix. This part is a unit matrix. 1, 1, 0, 0, right? This is a unit matrix. And this column is always a 0. So A looks like this. Here's a 0. Here's a unit matrix, but size n-1 times n-1. The whole matrix is n by n. Then this part is n-1. And here are the coefficients. Related with the coefficient of this part, or the coefficient here, or coefficients here. So I can put here y3 prime plus 2y2 prime plus 3y1 prime plus 4y. Now here, this one going down is -4. This one going down is -3, and this going down is -2. Depending on the order, if the system has this equation is longer, then the size will also longer, and here you have more coefficients. You need a times a negative here. You need a negative here. So 4 here's a -4. 3 here's a -3. 2 is -2. Alright. And the B will also will always looks like a 1 and 0 to 0, depending on the order. In our example here, the totally order is 3, so here I have 2 zeros. If the system has order, for example 10, then you have 1 is 1. Then all the rest, the 9 elements, they are zeros. And C. What is C? This is C, right? This is C. C is also here, you see? This is 2s plus 3. 2s plus 3. 2r prime plus 3. This 2 and 3, they are just here. 2 and 3 and 0. Here's a 2r prime plus 3r, and actually here is 0 times r2 prime. Then you just put a number here. This is C. As for D, okay, D should be here. In this example, I do not have. This is 0 times the input. This 0 give us D. D equal to 0 now, because this is y equal to something plus 0 times the input. Then this is 0. If this number is not 0, then here you will have that number. Here's D is just 0. If y is, you have something here. this will be 0 times the, now is 0 times the input. If here is like, for example, this is 9 times the input, then here will be 9. Here will be 9. But in this example, this is just 0. Alright, this is 0. Yeah, but this one you cannot find directly from here. You need after you do all, you give the structure, you can have this. If you have some pass here, this is 0. Now it's 0. This is D. This is D. Right? If Y contains something, contain R directly, no, just the times number on it, then this is D. All right. Okay. So this is a controllable canonical form. And we have different way to have the matrix form. Another one we call it observer canonical form. So I still use this example, but with this is method 3, which will give us observer canonical form. We still use the same equation, y with 3 order derivative plus 2 of y, 2 derivative plus 3 of y, 1 derivative, and 4 times y self equal to, what do we have? Okay, 2 of r prime plus 3r. Okay, alright. Then for this one, this time we will give a different kind of structure, but the idea is the same. We have the transfer function firstly. Transfer function, it will be 2s plus 3 over s cubed plus 2s squared plus 3s plus 4, and I divided by s cubed, both numerator and denominator. I have 2 over s squared plus 3 over s cubed in numerator, and denominator I have 1 plus 2 over s plus 3 over s squared and 4 over s cubed. Okay, then we use by the gain formula. We have structure. We use different way. The center part is the same. So 1 over s. I still need 1 over s, 1 over s, 1 over s. Then this will be the forward pass from input to the output. Okay, is this part? And I need a 3, so I put the 3 here. I need a 3 here, so I put the 3 here. And then we need another pass, right? Another pass. We only need 2 of 1 over s. So we will jump 1 of it. So now this time we will click like this. We jump across the first one. So in the second pass, we have 2 of 1 over s. So I have this s squared, 1 over s squared. And also I need a constant 2, so I put 2 here. Don't put 2 and 3 here, because you put 2 and 3 here, they contain both paths, right? Both forward paths go through this part. If you put 2 and 3 here, you will influence both. You put 2 here, this is just for the second path. And you put 3 here, this is just for the first path, right? Okay, so we have 2 forward paths. And then we need the feedback. Okay, here need a summation, right? It's going inside, so here's a summation. And then we need a feedback. We need a loops. We need to go backward. Now we go backward. We can use the backward. We need this part. We consider this. Which part is a common part? This part, right? This part is a common part of the system. Forward pass. I have 2 forward pass. Both go through this part. So the loop I use this as one of the loop. this loop is 2 over s. So negative 2 over s. Negative 2 over s. This is one loop. Second loop still contain these, but I needed one more s. Right? 3 over s cubed. So I can go like here. Alright, I just go to here. That will be fine, right? This is a negative 3. So we have second loop, right? This is second loop. Second loop, around this loop, I have negative 3 over s squared. So it is just this term, right? This is delta L1, L2, so minus L2, you get this. And similar, last one, 4 over s cubed. I will go to which part? I will go to here, but I don't want this is a negative 4. So here I put summation here. Alright, this 3 is before this summation. 3 is before the summation. That means along this loop we only have negative 4 and 1 over s cubed. Right? That 3 is in front of this summation. So it's not part of this loop. Okay, I put 3 here. I put 3 here. Alright. Is this good? This is summation. This is summation. Okay, now we have the structure. And we also need to set up x1, x2, and x3. This time we use x1 here. Yeah, we use x1 here. This is x1. We use the reverse order. In the CCF, in the controllable canonic form, this is previous one, right? I use x1 is here. The first for the first integral 1 over s, here's x1. Then this x2 and x3 in the most right side. And here we use the reverse way. I put x1 here. Then this is x1 derivative, right? The derivative go inside 1 over s. You will have x1. And then here's x2. This is x2 derivative. Here's x3. Here's a x3 derivative. Alright, by this way, you can also imagine, right? This is a circuit. You measure the value here as x1. You measure the voltage here as x2. You measure the voltage here as x3. Now, x1 take derivative is what? x1 derivative is here. It equal to a summation of x2 and negative 2 times x1. Right? So this is a negative 2 of x1 plus x2. Here I want to mention, like here as a summation, right? This summation, I didn't put the plus and the minus here. So this summation, it is just add 2 numbers together. If you put here is a negative, then this negative 2 you will replace by 2, just 2, no minus, but you put the minus here. It will be same thing. Alright. Okay, this is x1. This is negative 2 of x1 plus x2 give us x1 dot. The x2 dot, what is x2 dot? Similar, x2 dot is a summation of these 3 signals. X1 times negative 4, negative 3, right? X1 times negative 3, and x2. I have an x2. X2 dot is no x2. Then x3, yeah, just x3 plus x3, and the 2 of r. 2 of r. Alright, this is x2 dot, and x3 dot. X3 dot is here. It's summation of this signal and this signal. So this is x1 times negative 4 plus 3 of r. Alright, we have all the x state variables. We have the derivative equal to something. And then y is just x1. Okay, y is just x1, right? Y is x1. Okay, so we have our result. Now let's write it in matrix form. It is x1, x2, x3. Take derivative or equal to. Here's a -2 and 1. So this is a -2 of x1, 1 of x2, no x3. Here's x1, x2, x3, and plus no r. Okay. And the second line is x2 derivative equal to -3 of x1, no x2, and 1 of x3, and 2 of r. And x3 dot is -4 of x1, no x2, no x3, and 3 of r. Finally, y were equal to 1 of x1, no x2, no x3. Here's x1, x2, x3. Alright, so we have the result, looks like this. And we have the matrix. Okay, they are A, B, C, and D is also 0. D is 0, D is still 0. To compare with these, I put one more notation. Alright, this is controllable form, controllable canonic form. I put a C here. That means controllable canonic form, right? C is controllable canonic form. And this time we have observer canonic form, AO. AO is -2, 1, 0, -3, 0, 1, -4, 0, 0, and B, observable canonical form. This is 0, 2, 3, and C, this is observable canonic form. It is 1, 0, 0, and here's a D, still 0. Alright, we have this. Let's compare with the result here. For controllable case, you can see this is a controllable case, right? This one, this A controllable one is this one, and observable is one is. You compare these two, what can you say? You just transpose A, you can have AO, right? This one you transpose -3 go to here, right? The -4 go to here, -4 here, right? And here's a 1 is going up to here. No, 1 is here, and this one going up to here, to be here. Yeah, it's here, right? So this one and this one, you just do a transpose. So we will see A observable, B observable, C observable, D observable equal to A controllable, B controllable, C controllable, D controllable with a transpose. Right? It just you turn around, you get that one. You see, this is a B0, right? B0, B observable. Now it's a C, right? C just like this. And C now is the B. You just transpose. B go to this C0, you go to that side, it's B, and B go to that side, it's C. Yeah, they are transpose. Now D here is the same. D is the same. And you can also just look at this matrix itself. Then we can have AO will be some coefficient here. This is a unit matrix, n-1 by n-1. Here are zeros. This is n by n. And here a coefficient. This coefficient is coming from similar with that. We have y is 3 order plus 2 of y 2 prime plus 3y is 1 prime plus 4. Then here you have -4, -3, -2. Right. This number, these coefficients go to here. And B, C is just like this. C is always like this. And B, 0, 2, 3. This according to 0 times R2 prime plus 2 times R1 prime plus 3 times R. Then this coefficient go to here. This is B. VO, observable. Okay. C is always 1, then followed by some zeros. And D, well, it depends. Right? D depends. So in this example, it's 0. In this example, it's 0. Okay. So this is the observable canonical form. Yeah. Observable canonical form. The same equation. We are study the same equation. Same equation with different structure, different way to pick the state variables. Then we have different state equations. Okay, now we consider the fourth way. Another example. This is a method 4. We call this the model. How to say? It's a canonical form. Canonical form. It's a model canonical form. Canonical form is MCF. Oh, that is observable. Is OCF. This one for the method 3. This is observable OCF. Right. The controllable will be CCF. Oh, I put it CCF, OCF. This is MCF. MCF. We separated the transfer function into different part. This example. Okay, I suppose we have the transfer function now. We have T of S equal to like S squared plus 2S 3S plus 2 over S plus 1 S plus 2. I have S plus, oh no, just like this, S squared plus 2. Sorry, yeah, S squared plus 2 in denominator. In numerator, denominator is S plus 1, S plus 2, S plus 3 for this one. This one, of course, you can multiple these denominators, 3 factors. You multiple them, you have the times them out. You can have a polynomial of 3rd order in the denominator. Then you can have the CCF and OCF. Okay. But now we use the partial fraction. We write these as A over S plus 1 and B over S plus 2 and C over S plus 3. Then we can have what is A, B, C. We multiply denominator in both sides. We have S squared plus 2 is A times S plus 2 and S plus 3 plus B times S plus 1 and S plus 3 and C times S plus 1 and S plus 2. Alright, yeah, I don't have enough space here. Okay, then let S equal to -1. -1. Then these two terms will be 0, right? S plus 1, S plus 1. So I have -1 squared is 1. 1 plus 2, I guess 3, equal to A times -1 and 2, I get +1. -1 and 3, I get +2. So totally is 2 of A. Then B 0, C 0. So we have A is 3 over 2. I have A. Let S equal to -2. -2, here's a square is 4. 4 plus 2 is 6. -2, this is 0. -2 here, I have -2 plus 1, I have -1. -2 plus 3, I have +1. So -1, +1, that is -1. And S is -1, S is -2, this is 0. So we have B is -6. Am I good? -2, I have -B. Yeah, okay. B is -6. And let S equal to now is -3. So this is 3. 3 is 9 plus 2 is 11 equal to S plus 3 is 0. S plus 3 is 0. Then I have C with S is -3. So this is -2, -1. So positive 2. So I have C equal to 11 over 2. Okay. Alright, I have A, B, C, right? So we can have T of S equal to A is 3 over 2 times S plus 1, and B is -6 over S plus 2, and C is 11 over 2 over S plus 3. Okay, now we have structure. We can base on this, we have structure. We have 3 parts. So the structure can be like this. This is a 3 over 2 S plus 1, -6 over S plus 2, and 11 over 2 S plus 3. Now we can have a structure looks like this. And of course, what is this? S plus 2 over S plus 1. We still need to give the structure of this piece. Each piece, we have 3 pieces, right? Small parts, 3 small parts. Each one, we can write, okay, we have 2 choices. We can use either CCF or OCF. For example, we use CCF for each. Then we can have this one, we have 1 derivative. So we have 1 loop, right? You divide by S, you need 1 loop, 1 forward pass. Oh, this is just 1 forward pass, 1 loop. You need these. You need 1 loop. Right? This should be divided by S. It's 1 over S. So this is just -1. -1. So it's 1 loop. This is denominator. Numerator you need times 3 over 2. So you put 3 over 2 here. 3 over 2. Okay. 3 over 2. It's clear? 3 over 2 here. Okay. So this is this part. And the second part, this part, similar. This is just one of this 1 over S. And here you need a -6 here, and here you need this is a 2 over S, right? 2 over S. You divide by S is 2 over S. 2 over S. This is 1 over S. Here you need a 2 over S. -2. Yeah, I put -1. You can also write in this way. Put a triangle. Okay. And the last one, similar. Summation, here is 1 over S, and the forward, here is 11 over 2, and here is a feedback with -3. Alright, so you have these 3 parts, and the input side, the signal separate to three paths, 3 branches, and finally you need to add these 3 together. So this is a input, this is output. You have things look like this, and then you give the matrix. Before that, you need to choose, like this is x1, then this is x1 dot. You always have this. When you have a 1 over s, then the two side, the output side will be a signal, and then the other side will be the derivative of that signal. Similar here will be x2, then here will be x2 derivative. Here's a x3, then here will be x3 derivative. Then we can have x1 derivative will equal to summation of these two, right? Summation of these two. It is a x1 with negative plus r. x2 dot equal to x2 times negative 2, x2 times and x2 plus r. And this is x3 dot. x3 dot will equal to negative 3 times x3 plus r. And output y will equal to 3 of x1 minus 6 of x2 and plus 11 over 2 times x3. 11 over 2 times x3. I think I make something wrong. Oh, here, this one is 3 over 2. This is 3 over 2. 3 over 2. So here's 3 over 2. Alright. Okay. So finally we have these equations. And in matrix form, we have x1, x2, x3, take derivative equal to negative 1 of x1, no x1 times negative 1, no x2, no x3, x1, x2, x3, and plus 1 of the r. And second line is a negative 2 of x2, no x1, negative 2 of x2, no x3, and plus 1 of r. And the third one is I have no x1, no x2, and the negative 3 of x3, and plus 1 of the r. And y will equal to 3 over 2 of x1, negative 6 of x2, and 11 over 2 of x3, x1, x2, x3, and plus 0 of r, the d is 0. And we have this. So this is a AM, this is a BM, this is a CM, here's a DM. Alright, DM 0 in this example. Okay, here the feature is AM, the model canonical form. AM will equal to negative 1, negative 2, negative 3, 0, 0, 0, 0, 0, 0. So you see, you have these three blocks in the diagonal, negative 1, negative 2, negative 3. Yeah, you separate. You can say it's separate like this. Separate like this. You can also say, look at here. You can think you have 3 separate systems. The first one, it just contains x1 and input. So you can think this is a small system. R is the input, x1 is output. Okay, this is small system, only contain R and x1. Second equation also a small system, contain R and x2. Similar. Third one is also a small system, subsystem. So we have three subsystems. They combine together. You do summation with certain coefficient in front of this output. You have y. Right? You look at the structure is also like this. You have three small systems. You combine them together. Use a parallel way to connect them. Then you have the output. This one gives you the whole structure. And finally, you have equations. You write equations based on this. You won't have this one. You will have the model canonic form. All right. But this method is not uniquely. Now I separate the system as three pieces. I can also separate it as two pieces. Another MCF, model canonic form. Where's the problem? Problems here. Yeah. Problems here. Right? We have T of S is this. Now T of S equal to, which is S squared plus 2 over S plus 1, S plus 2, S plus 3. I write this as A over, I times the first two together. I have S squared plus 3S plus 2, AS plus B, and C over S plus 3. I write it in this way. Yeah, I can write it in this way. This way will give us, actually, it's just I combine these two together, right? I combine these two together and keep these separate. So this will be, I just use this one. I combine these two together, so this will be a fraction. Here's a S squared plus 3S plus 2 in denominator, and numerator is a 3 over 2 times these minus this one times these. So I have negative 6 and positive 1.5. So I have negative 4.5 S. And 2 of these is 3. 3 minus 6 is minus 3. Right. This one, the first part. The second part is the same thing. So we have these. I can have these. Then by this way, we can have the structure look like this way. I put the simple one in the top. Here's 1 over S, 11 over 2, and here separated with feedback. The gain is negative 3. This is the top one. And this one, I need a larger one. I need a 2, 1 over S here. I have 2, 1 over S here. Right, this is Y, this is R. And you can use the controllable canonic form or observable canonic form. Suppose I use controllable canonic form. I have 2 of these, and the forward pass, I have 2 forward pass. So one is these, another is these. Right, and this part, right, this one. And then I need 2 loops. So one is one loop here, and one loop is here. Okay, the loop, this loop is negative 3, and this loop is negative 2. Okay, am I good? And I need to put the forward pass. This one with, this is a negative 4.5, right? I divide by S squared. I have negative 4.5 over S. This one over S, and negative 3 is here. I put 3 here. 3 should be here. In this part, it's a 3. And before I times 3, I need a feedback. Okay, So I have structure looks like this. Then you can have the system. I use this x1, x1 dot, x2, x2 dot, x3, x3 dot. Then I have the equation. Okay, it's the time I'm done. So x1 dot equal to summation of -3 times x1 plus r, right? x1 dot equal this one plus this one, and x2 dot is a summation of three signals. One is r, one is from x2, one is from x3. So is -3 times x2 minus 2 times x3 and plus r. This is x2. And x3 dot okay, just x2, right? Just equal to x2. And y will equal to summation of these two signals. X1 times 11/2 times x1, and here will be summation is -4.5 times x2 and 3 times x3. Alright, so we have the equation looks like this. If we put them in matrix form, then we have x1, x2, x3, take derivative, that will be -3 of x1, no x2, no x3, x1, x2, x3, and plus 1 of the r, right? The first equation. Second equation, x2 dot is -3 or no x0 or no x1, -3 of x2, -2 of x3, and 1 of the r. Then x3 equal to x3 dot equal to no x1, 1 of x2, no x3, and no r. Okay, and y were equal to 11/2 -4.5 and 3. The coefficients here is x1, x2, x3, and plus 0 times r, d0, right? d0. You see, this is now this time you separated the system as two part like this. The first one and this first one, these three, they related with this part, this subspace, subsystem, and x2, x3 related with this part, and this part. This is x2 and x3, another subsystem. Alright, so this is also a model canonical form. So model canonical form is not unique. You can choose different way to separate the system as combine of parallelly of some subspace subsystem. Then you can have different MCF. Alright. Okay, that's all for today. See you next time. Actually, see you next week, and I will put few problems for the homework of this part. Alright. Okay. Bye bye. Have a good weekend.